it is time to start the second plenary session. I am Kwon Levan, I am Vice President of APET, and I'm very pleased to share with Humberto Moreira the presentation given by Professor Hugo Hopenhayn from the University of California. Humberto will introduce Professor Hugo Hopenhayn.
Okay, thank you. It's really a great honor to me to introduce Professor Hugo Hopenhayn. Hugo Hopenhayn, as you may know, is a prominent economist who has made deep contribution in different and important fields of economics as mechanism design, industrial organization, macro theory, and labor. Professor Hopenhayn is Argentinian and has graduated at the University of Minnesota in 1988. He is nowadays a professor of economics at the University of California, but he still keeps strong links with Latin America. Hugo has consistently published in top journals of economics through all the years, especially, still keep active, publishing very good piece of papers, in very influent journals. Just to give you an idea, his solo paper in 1992 in Econometrica, whose title is Entry, Exit, and Firm Dynamics in Long-Run Equilibrium, has almost 2,500 citations, according to Google Scholar. This, that is not a perfect measure of impact, but it still is very impressive how much the type of work Hugo Hopenhayn has been working. More importantly, his contributions have influenced the way economists think about important topics like patent and employment design and firms' dynamic under financial frictions. I myself, unfortunately, I did not have the chance to see Hugo presenting many times. This is going to be one of these times, and I'm grateful for that. But I remember there was a meeting, I was just commenting with Hugo in Rio some years ago. I cannot be precise exactly the year. And Hugo had to do the discussion of Cherry's paper. Cherry is a distinguished professor at Minnesota University. And from that discussion, and what struck me a lot is that he built in that discussion Cherry's paper in a very nice way, in a very brilliant, intelligent way. Not only that, but he pointed out the problems that the paper had. And I said to myself, gosh, I have to rethink the way I do research and even my discussions from now on, because it was so impressive that I was completely struck with that. So with no more words, I would like to thank Hugo Hopenhayn to be here presenting one of these challenging and beautiful papers, I believe.
Well, thank you very much for your presentation, your kind words. It was nice to have the opportunity to criticize an old friend, Chari. And also, glad to be participating in this sort of important celebration of Aloysio's birthday, and being back again here. I think it's the first time I'm in Getulio Vargas, actually. I mean, I've been in Rio several times, in conferences, but here I think it's the first time. So being here for the first time, and to talk about something that I've been working out lately, and I'm kind of excited about. And I guess excitement goes with learning. I learn things, and I sort of develop new intuitions about a problem that I had no idea. And so I think I hope I can share that today. So this is a paper with Francisco Squintani, on which we have been writing a series of papers on patent innovations, more from the perspective of normative and the normative side. And this is a slightly different paper, and I'm going to put here Maskin's. I'm following on Maskin's suggestion with Partha Dasgupta in 1987. of course, you work on a topic, and then after you've, proved your theorems and so on, you said, okay, let's look at the literature to see what they said before. And then you find a paper that, had basically, said, here are the important questions, and then you're worried after you read the introduction that then come the answers. Fortunately, we had some different approach to the problem, and so I think I'll be able to provide novel answers to these questions that were raised at the time, and I think the literature on innovation and patents did not follow, so closely, and they should have. Okay. So here are the questions that they set up. What problems had to be on the agenda? And by the way, I also have this view of being, thinking about innovation as solving problems. So there are a series of problems, and this could be in our field, could be in sort of R&D or whatever. And there are these problems that we are going to try to solve. And solving the problems has rewards, both private and social. And so what problems ought to be on the agenda? This sounds like, the direction of innovation. How many and what kinds of research projects or research strategies ought to be pursued in tackling them? How ought resources to be allocated among the chosen research projects? And the problem that I'm going to consider is precisely a research allocation, an allocation of endowment of researchers or research inputs across projects. So it's exactly that. How ought to be conducting the research, and how ought research personnel to be compensated? These are questions that I'm not going to talk about, but that have been part of the central piece of research that has been done on innovation. Okay. So after this, let me sort of if you go back to the sort of last 20 years of research in R&D and innovation and in patent design, the debate mostly that you find is whether patents are weak enough, strong enough. It's kind of boring at the end, whether weak enough, strong enough, and is there are they giving only rents to firms, or are they giving too little incentives for innovation, et cetera, et cetera? And there are advocates on both sides. That's the too little and the too much side. And a question that has been less considered, which is a question that I think that you were fundamentally interested in, is the direction of innovation. Like, are resources for innovation going to the right places? And that's a question that we raise here, and it's a question that we're going to try to understand from the perspective of a very, very highly stylized model, and sort of, I'm going to try to progress along, in stages, going from a sort of static description of the problem of allocation and link it to the literature on congestion. And then I'm going to introduce some dynamics slowly, or at least what I would consider slowly. I'm going to do some dynamics, and there's where we're going to find some new intuitions. Okay, so our basic theory will have heterogeneity and I should say the heterogeneity that literature has, starting from Eric's paper, considered was more on sort of research methods, and this was the idea of, in order to find questions to the same problem, there might be different ways of doing it, and there may be competing ways, and so some closer, some further apart, and that's kind of where the research has been sort of focused. And I'm saying research that was done a while ago because it's not really the most active area in R&D or in patents. As opposed to that, I'm going to consider a different question, and there's going to be a series of, if you want, patent races, and which are not competing with each other. Each of them is a patent race, so it will attract researchers that will be competing within that race. But the question I'm going to ask is more a question of, in these non-competing patent races, except for they're competing for the inputs of researchers, are the set of inputs in research allocated across these different questions in the right way? And that's the center of a question. Of course, especially many of you that are trained like Aloisio in general equilibrium, and many of you that are students of Aloisio, always are suspect when one says, I'm going to compare competitive versus optimal allocations, because we're kind of trained in the first welfare theorem, and I was also trained in that. And so I am going to find, and we're going to find here, that there is a gap between the competitive and the social planners or optimal allocations. And the reason is quite simple, a missing market. And if you think that market is not missing, then this is the end of the talk. And you can leave, without any problems. But the market that is missing is what we think is the market for problems. The problems are out there. It's like in our profession. Nobody tells you you can or cannot work on a problem. And the problems are out there. There's no property rights on those problems. And whoever solves those problems gets a return. And I'm going to take, in the same spirit as Eric's paper, I'm going to take a winner-take-all perspective. So the first to solve a problem, let's say, is the one that takes the returns of that. So that's going to be the basic source of failure. In terms of the heterogeneity, I'm going to consider only one dimension of heterogeneity. In the paper, we also look at sort of the dimension of difficulty, but I'm going to assume that all papers are as easy to write, no, that all problems are as easy to solve. So in that sense, problems are symmetric. They're independent. And what differs across problems is the price, the return. So there are hot problems and there are problems that are cooler, or cool, not cooler. Cooler are the hot here. So that's going to be the variation we're going to have. And so the hot problems are going to be problems that have higher social and private value. So we're not going to make the distinction there. And that's the question we're going to consider. And the result that those equilibrium allocates scarce researches to different patent races. So I'm going to consider one input only. That's obviously without loss of generality here. The equilibrium and optimal allocations will really coincide. And we're going to get, in general, under plausible assumptions, too many researchers in hot areas. So somebody was telling me that, whenever a new data set appears, then, all empirical economists just like run to try to be the first ones to, get the first paper published with that data set, And here, there is going to be a distribution of researchers across problems, but competitive equilibrium will tend to allocate under certain assumptions and for different reasons that I'm going to go through. Some, static, some dynamic. Too many researchers in the hot areas. Okay, so that's there's a large literature, going back to Arrow and probably, earlier on too. And the idea that knowledge is a public good and the problem obviously of being able to create incentives for the creation of knowledge in that context. Was a long literature, it's not anymore that active in the 80s on patent races. In the patent races, usually the literature was there was one patent race, and the questions that were raised in that context were more about the speed of discovery, the competition between the participants in the patent race, and an idea that was there, deep down, which is a rent dissipation, that because there tends to be excessive entry into these patent races, to the point that, when entrants obviously do not consider the fact that they're reducing the probability of others of achieving the success, and that leads to excessive entry. That was sort of something that was embedded in this patent race literature. So in my case, I'm going to consider an inelastic supply of researchers. So there is a sense in which there cannot be excessive entry. There can only be excessive entry in some areas and maybe too little entry in others. So what I am going to be considered is the impact of this, this rent stealing, if you want, on the distribution of researchers on patent races, and also from the dynamic perspective. So the plan of the talk is I'm going to start with a simple model. I'm going to start with a static problem, and it's a very simple allocation problem, and I'm going to bring in dynamics slowly into the problem. So in this static problem, think about there being two research areas, two problems to solve. Think about two patent races, and one potential discovery in each. The social and private value of discovery are going to be Z1 for the first problem solved and C2 for the second one. So problem 2 is the hot problem, problem 1 is the cool problem. So we're going to assume here that both the private and social value are the same. what we're really, the assumption that we're making is that that the share of private to social value is the same across these two patent races. And we're making this assumption not because we think it's a realistic assumption. It's very easy to generate an incongruence between the competitive and the social allocation if you assume that these, the appropriation varies across different races. That automatically, in principle, will immediately generate a gap. So we're not interested in that one, so we're trying to illustrate a different one. So we'll take this extreme assumption that, we essentially, assume away that problem. There's a total exogenously given set of researchers, call that capital M. And the structure is very simple. There's a probability of discovery function, and it's a function of the number of researchers here, M1 or M2. And this is a total number of researchers in each of these areas. So, and it's, as I said before, for simplicity here, we're assuming that it's the same across these two problems. Okay, that's the basic structure. So the economic problem is essentially to take this set, this endowment of researchers and split it between, these two activities. Okay? So for the competitive equilibrium it's fairly straightforward. These researchers, if there's going to be an interior solution, are going to be indifferent between going to one area or the other. So what is the expected return of a researcher for entering a particular area of research? So PMJ here is the total probability of discovery divided by the number of researchers, and assuming that all are equally likely to succeed, that gives the probability of an individual researcher, the ex-ante probability of being the winner in that area. Okay. So if you take those probabilities, multiply them by the respective prize associated to winning the race, then this condition simply says that the expected return of being in each of the races has to be the same. Okay, the expected, it's the average return. Okay. The social planner, on the other hand, maximizes the total expected value, which is given in this second line or whatever. And obviously the condition, the optimal condition for that is to equate the marginal returns in the two areas. And these rarely equating marginal returns and equating average returns, unless you have like a constant elasticity function, will will disagree. Okay? And this goes back to literature of congestion. I mean, when there is congestion and there's alternative roads, then you might not expect, in the competitive equilibrium will equate, let's say, the average time it takes on each of the roads. The social planner would like to look at the marginal time or marginal effect on total time on each of the two, and they're rarely going to coincide. Okay. So a key ratio is this of this wedge is the ratio of the average over the marginal. And in some sense, this represents the relative importance of the business stealing effect, if you want, or the rent stealing effect over the social marginal value of the input. Okay? So the higher this is, in some ways, the more rent stealing there is. And this is sort of a key ratio wage. And the result, and this is really not a deep result, but the result at this stage says that you're going to get excessive entry into the hot areas, and this would be, in this case, area 2, if this ratio between the marginal and the social is increasing in M. Okay, so this follows directly from intuitively, this follows from the fact that it's always going to be the case that both the equilibrium and the optimal allocation will assign more researchers to the more productive area. Okay? And so the more productive area will be the one that always, or the hot area will always be the one that will have higher M. Now, if this wedge is increasing in M, it's the one that will where this distortion will also be higher. And that's the intuition behind this argument. So this wedge, which is the inverse of the elasticity of the probability of success function, if it's increasing in M, then you're going to get excessive entry into the hot areas. Of course, if it's decreasing in M, you're going to get the opposite result. So what I'm saying, this is not like a super strong result. It relies on a specific assumption on the discovery technology. Okay. So what I'm going to show next is that in some ways, and this is a bit literature driven, but that the model that people have been using in these dynamic patent races is one where this condition is satisfied. And so the sort of that canonical model would lead to excessive entry into the hot areas. So the first I'm going to do is I'm going to take this and put time into this problem, so translate it into a problem of time. Actually, there is an intermediate step, which maybe is not that interesting, which is just I took two areas here, 1 and 2, that generalizes to having like a continuum of research areas with a distribution f of return. So f of z, it would be the CDF for the price or the return. And kind of the same principle applies. Here we're going to say there's going to be an allocation. When I put the tilde here, that represents the optimal allocation. The other one is the competitive allocation. So this is what we're going to say there's a bias to hot areas. It's a single crossing condition, and it's a condition that says basically, if you look at this picture, above a certain threshold, there's going to be higher allocation of resources in a competitive equilibrium. Below that, more on the social planner. Of course, this has to be that way because they all both have to aggregate to the total endowment. Okay? And so this is when we're going to say that there's excessive entry into hot areas. And the condition for getting this in the static case is exactly the same as before. It's the wedge. Condition is that if this wedge is increasing in M, then you get excessive entry into the hot areas. Okay? So now I'm going to go to the sort of start putting in time. So I'm going to take basically what's going to become later the sort of a model of where there's going to be redeployment and reallocation. But I'm considering a situation where there is time, but the allocation of researchers in each of these activities is chosen at time 0 and cannot be changed. Okay, so this is a case, where people are super specialized and they can always only write the same paper over and over, and I mean it happens, And so this is, this model. But next stage in putting dynamics into this will be thinking about, well, when some people finish solving a problem, they can start working on another one. And so people not being that specialized. Maybe there's some cost of starting. You have to read things. You have to get in, up to the frontier and so on. So we'll get to that. So first then, MZ, so the researchers that are allocated to a particular level of innovation Z are chosen at time 0. The line ends with discovery. So when discovery occurs, that's it. That ends, and the researchers in that line become idle. So there's no redeployment after discovery. And the structure now is going to be just, rather than having, as we had before, we had P of M, now it's going to be a density. If you put M researchers working on a particular activity, then this is the density over time density, or distribution over time of the discovery. Okay? And as usual, now assume that if you increase M, then you're going to stochastically earlier, so discovery will occur earlier, and so on. Okay? So that's the flavor of things. So if you think about the welfare function, is going to be the integral of the expected utility across the different lines of researchers. So these are the ones indexed by Z. And for each of these lines, it's fairly straightforward. The expected utility will be just Z, which is the return in that activity, multiplied by now an expected discounted time. And so the right-hand side of that, x of minus RT, that's just the standard discount factor, and multiplied by the probability that things occurring exactly at time t. So now it's not a matter of whether you discover something or not, but it's a matter of time. So more researchers will speed up research in that area. Okay. So if you take this problem and you just redefine what we had before, P of M, as the expected discounted sort of probability, expected discounted time, if you want, of discovery, this P of M now, put it in there, and you get exactly the same objectives as before. So the question now is whether this P of M satisfies the property that the mean over the marginal increases in M, and that would lead to excessive resources allocated to the hot areas. Okay. So here's an example, and this is a canonical example that people use for this P of M, which is a Poisson model of sort of research discovery. And so in the Poisson model, there's a arrival rate, which is lambda, which is common to anybody that works in that research area. And so the instantaneous arrival rate, assuming independence across researchers, which is the common assumption in that literature, would be m times lambda. And so the expression for PM that I had before, I won't walk you through the steps of this, but that's sort of a very simple expression. Notice, by the way, if R is equal to 0, this is equal to 1. I mean, so there, it really doesn't matter. And that's trivial. If R is equal to 0 and, planner doesn't discount the future, as far as all these are discovered at some time, it's the same. Yeah. So the key ratio for the proposition, if you work it out, ends up being the one down here. That's increasing in M. So this canonical model has embedded this property that you're going to get excessive research into hot areas. Okay. In the paper, we have some calculations and trying to get some bounds, like numerical bounds. Having a little leg in macro. In my case, I like to put numbers to things and have in a Pareto, for the case where there is a Pareto distribution of the C's, we get about 20% of gap between the sort of in terms of welfare between the private and the competitive equilibrium and the social planner. Okay. So now we're going to start, thinking about redeployment. So once a project is solved, then researchers can be reallocated. So let's go back to our simple previous example. There's these two lines of researchers, and let's take the Poisson model. And from now on, I'm going to stick to the Poisson model, and just because it's very tractable and very simple to work with, though I know that it's biasing in some ways results. I'll get back to that later on if I can. And now, what we're going to assume is that there's some cost of redeployment. Basically, you're working on a problem, you solve that problem, let's say, or somebody solves that problem. Now you want to start working on a different problem. Well, you have to pay a cost. So it could be small cost. And that you can interpret it as, cost of catching up, have to read books, you have to talk to people, you have to go figure out things. Okay? Catch up to the frontier. So, and what I'm going to assume is that researchers can redeploy immediately after the first arrival. I mean, results really are not too sensitive to that assumption. And for to make the arguments more simple, I'm going to think about there being many researchers, so being small relative to the population. So the allocation will involve, and I'm going to consider that the costs are sufficiently small so that once one problem is solved, everybody goes and works on the second problem. So those that were already there, and the ones that were working on the one that was solved. Okay. So the allocation is going to be then very simple. At the beginning, there's going to be M1 and M2 researchers like we had before, working on problems 1 and 2 respectively. And then immediately after arrival, everybody will switch, or the ones that solve the problem will switch, and then everybody will be working in solving the second problem and last to be available. Okay. So that's the allocation. So I'm going to run you a little bit through some equations, at least try to give you an intuitive feel for this. So this is working backwards. When the first problem was solved, now we have all researchers working on the remaining problem. Okay. So we can calculate, well, what's the expected value for me if I'm one of those researchers? Okay. And there's a discount factor which is associated, this one first, and the m lambda over r plus m lambda, which is associated to the time of discovery. So that's simply the time of discovery, meaning the time at which the first one to discovers that. So that's just discounting. And the other part, Ci over m, is, well, with probability 1 over m, I'm going to be the person discovering that. And the expected payment will be Ci times 1 over m. Okay, so that's what it is. And it has this very simple form in the Poisson case. So now we can go back to sort of the first period, or the beginning of time, and we can calculate what are the value functions or the value of entering into each of these two areas of researchers. So that's what's going to be equated now. In competitive equilibrium, researchers at the beginning must be indifferent between going to line 1 or 2, assuming we are in an interior equilibrium. Okay. So let me walk you just a little bit over the first equation. The first equation corresponds to the value of being in 9.1. There's two possible events here, which are the problem 1 is the first one to be solved, or problem 2 is the first one to be solved. So the first term here corresponds to problem 1 is the first one to be solved. And this term here incorporates both discounting and the associated relative probability of that being solved. So in that case, if problem 1 is the first one to be solved, and I'm working in problem 1, I have probability 1 over m1 to be the one that solves that, multiplied by z1 is my expected value. Then I get the continuation value v2, because I'm going to join now the group of everybody solving now what remains to be solved, which is problem 2, and minus c, because I have to pay this cost of switching. On the other hand, if the second problem 2 is the one that is solved, then I'm not working on that problem, so I get no returns from that. But I only get the continuation value, and that's V1. Okay? So the same way you can write a similar equation for problem 2, equate these two, and if you equate this two, you get a very simple condition, which is that the difference in return, C2 minus C1, has to be equated to this difference, M2 minus M1 times C. What is this condition? This is what you might think of as a value burning condition. Is C2 minus C1 is sort of the difference in payoffs that you get if you are the winner of solving problem 2 versus problem 1. So that's the difference in returns. To offset that difference in returns, something must happen. So what is to happen here to offset that is that the probability of the area 2 being the first one to be solved is higher, and so as a consequence, if you are in that area doing the research, you're more likely to have to pay this cost of switching. And so that's the only difference. This is M2 minus M1. This sort of the relative probabilities of being one or the other is M2 minus M1. This is true, by the way, if you think about instantaneous probability in the Poisson case. Okay? It's that times lambda, and lambda would be on both sides. And that times C is how big the gap in the two have to be so that you are more likely to be the one that will have to pay the switching cost if you go to the more attractive problem. And that, in essence, is, if you think about value, since value are equated, is what is burning in some way the difference in values. Okay. So value burning occurs here, but occurs not in total because we have an inelastically supplied set of researchers, but occurs across these two activities. So for the social planner, the difference between the social planner and the competitive allocation, of course, is that the social planner doesn't care who gets who gets to win. So for the social planner's perspective, that's not divided by M. I'm not going to walk you through this because I've gone through my equation, but you can again write the social planner's problem as a period 1. Including, again, the two possible events, allocations of M1 and M2 respectively. And if you sort of take the first order conditions in this problem, this is what you get, okay? So let me compare the two, the optimal and the competitive equilibrium. And here are sort of the main insights of the dynamic problem that will come back when I look at the next I'm going to do, look at a sort of a, kind of do the same thing as I did before, start with a larger set of problems that are being solved over time, stochastically. And then I'm going to look at a sort of a stationary equilibrium where new problems are coming into society to being solved. And so at the end, there's a stationary distribution of problems that exist that takes into account both the inflows and the outflows of problems. So that's sort of the step. But this insight is going to be pretty much exactly the same. The formulas are going to look a little bit different, but the intuition is going to be the same. Okay? So if we look at the difference between the two equations, the first order condition of the optimal and the second one, which is the competitive, we can see that there are two differences. Okay? One is that there is a term, 1 minus lambda m over r plus lambda m, which is a term which is less than 1, which is multiplying the C2 minus C1. Only when r goes to infinity, this term will be equal to 1. But if r is not infinity, so if there's not total impatience, if you want, this term will be less than 1. So that said, the social planner in some way is underscoring the difference between the values of these two lines of research. Okay. What's the intuition behind that? From the social planner's perspective, if the good problem is not solved first, well, it will be solved later. So it's a matter of time, and that's what it takes into account. In some ways, from the social planner's perspective, if a good problem is not solved early, then the continuation value is higher because now there is a good problem to solve in the future. And so good problems are like better assets. Here, the technology for production of a sort of knowledge or value takes the asset, which is the problem, and takes researchers, which are the other input, and as a result of the two, we get production. So if a good asset stays, a better asset remains than a worse asset, that has value for the future. So the planner, in that sense, discounts the difference between these two. Okay? Only, as I said, in the extreme case where the planner is super impatient, they will be the same. Why in the equilibrium that's not taken into account? And this will go sort of I'll give you the sort of intuition that carries through the more general case. In some ways, from the perspective of a competitive equilibrium, all problems are the same. And they're the same because the market takes care of equalizing the value of them. So from the perspective of competition, what problem remains, or the set of problems remains are going to be the same, given that values are going to be equalized. Whereas for the planner, it's not the case. Okay. So that takes care of the left-hand side. The market overstates relative to what's optimal the differences between the returns of these activities. And then we go to the right-hand side. So on the right-hand side, basically, the only difference is, except for the fact that I wrote them multiplied in the opposite way, but the only difference is that 2 that appears there in the social planner, and only 1 in the case of. And this is a very sort of a standard externality, maybe you can call it duplication cost, which is basically when I privately decide to work on a problem, let's say a problem 2 instead of problem 1, I'm increasing the what I look is, if there's more people working on problem 2 than on problem 1, that means that I'm more likely to have to pay that cost of relocation. And M2 minus M1 times C captures that. Okay? The effect that I don't capture is that when I join a research area, I make it more likely that there's going to be discovery in that research area, and that everybody that is doing that research area will have to pay that cost. Okay? So when I switch from 1 to 2, that's sort of I'm exerting that externality in more people than in sector 2, then I'm exerting that externality in sector 1. And that's what it's capturing. And if you go back to the social planner, there's going to be here this M1 times M1, there's going to be a square there. And then when you take the derivative, you're going to get the 2C. But that's intuitively what's happening. Okay. So there's going to be excessive entry to hot areas for 2 reasons. And these reasons, by the way, I think are very robust, don't depend on the specification as much on the specification of probability of discovery function. We proved this in the case of Poisson, but we believe it's a much more robust intuition than just the particular properties of P. So there's going to be excessive entry into hot areas for 2 reasons. One is what I call the option value effect. If something is not discovered today, there's still an option value of discovering in the future, whereas the competitive equilibrium doesn't take that into account. And this negative switching cost externality, which is the marginal cost of redeployment, is greater than the average cost. Okay, so briefly, let me walk you what happens when there's sort of, again, the continuum of lines, not only 2. Not much in terms of new intuition. The equilibrium will look like this. There's going to be an allocation, MTC. This is at time t, how many researchers are allocated to a problem of time z. Okay? This is going to be increasing over time. And the intuition is there is a ratio of researchers to problems. As problems get solved, that ratio goes up. So researchers become a less scarce input. And so it's going to be efficient and optimal, and also true in the competitive equilibrium that more researchers are going to be allocated to each of the problems. Yeah. And that is why this MTC is going to be increasing over time. As a result of the allocation of researchers across these different research lines, there's going to be an evolution of the distribution. This is G of TZ is the CDF of the problems that are left at T. So we're dropping out all the problems, and of course, if M is increasing in Z, we're going to be dropping more problems at the high end than problems at the low end, and that's going to dictate the evolution of this distribution of problems to solve. Okay. So from the perspective of the competitive equilibrium, or the competitive allocation, and this is in flow terms, the value of working in Z, I inverted these, in a problem Z at time T. And it's basically the instantaneous, this is a flow equation, so you can interpret this sort of in terms of equivalent sort of flows. The first term being the flow associated to discovery, so the arrival rate of discovery is lambda m. If you're the one to discover, then you get Z, or the probability of that is 1 over m, you get Z, and then you pay the switching cost C. On the other hand, what's going on too is that the value of being in an activity is going to change over time. And it's going to change over time precisely from what I said before. More people are going to be coming into your research activity, so you're going to be competing with more people. And so the value of being in that is going to, actually VT is going to be negative. It's going to decrease over time. Now, of course, all those research areas where there's entry of researchers will have this VZT being the same. It will be indifferent between the two. So the left-hand side will be the same. But if it's going to be the same for consecutive periods of time, the right-hand side, the derivative of that with respect to T, also has to be the same. So if you equate both the left-hand side and the right-hand side, all what you get is, that across the research areas, that the middle term also has to be equated. Okay? And from the middle term being equated, what we get is that C minus mz of C has to be equated across active Z's. This is exactly the same condition we had before. The difference in Z's has to be outweighed or compensated exactly by the differences in M's multiplied by the cost. It's exactly the same condition. Okay? I'll skip this. So the optimal allocation, the way we calculate the optimal allocation is the following. We say, okay, let's give property rights. It's kind of giving property rights over the market that we know that was closed before. So let's give property rights over problems. So think of problems as islands, if you want. These islands are owned by a firm. The firm makes a hiring decision, so it decides how many researchers to hire at every point in time. And I'm going to assume, to make it simple, that it makes, when the research is finalized, it pays the switching cost to research. I'm going to implement it that way. Okay, so this is the corresponding expression. And once you sort of solve for this and get the first order conditions, there's a multiplier that will correspond to like a rental rate of researchers in this competitive implementation. And what you get is the first term. The second term is the competitive equilibrium. The first term. So if you see, if now, again, the comparison between the social planner and the competitive equilibrium, for the competitive equilibrium, what we have is on the left-hand side, this is, I've expressed it in marginal return. So, the return of increasing a Z by 1 unit. So this is like we had before, C2 minus C1. Think about being 1, that difference. Okay? So that's the extra return per unit of Z. On the left-hand side, on the upper term on the left-hand side, we have this term for the social planner, which is discounted by the residual marginal value of Z. It is basically saying the social planner, again, understands that the an open problem that of a higher C has more future value. It has marginal value. And so the cost of solving a problem is that you lose the asset, which is the problem to be solved. And so that's a cost that the planner takes into account and diminishes the return from the investment. And then on the right-hand side, we have the switching cost externality, 2 times C instead of just C. Okay, so it's exactly the same 2 effects as before. So the final step is a steady state analysis. I mean, not much new is going to be obtained here, except that I'm going to be able to do some calculations. And in particular, I'm going to be able to do some calculations of welfare between the competitive and the social planner's case. And I'm going to do it in a way which is not the most the most compelling way, because you might think that the way perhaps things work, or one way things work, is as problems are solved, new problems are opened up. In models of innovation quality ladders, that's clearly the case. No? And, once you make a discovery, then you can make now a discovery that sort of adds to that one. Okay? So rather than having that, I'm going to have problems arriving exogenously. And more importantly, I'm going to assume that the type of problems that arrive is just exogenously drawn from some distribution. As if somebody is kind of grabbing, and just throwing us problems, to be solved. Okay? This is essentially identical to assuming that every time a problem is solved, a new problem is created, but that new problem has zero correlation with the type of the problem that was solved. Okay? The extreme other assumption would be that it's identical to the problem being solved. Okay? The results that I'm going to get here are very similar if we have some mean reversions, and meaning that if you're solving a really hot problem, maybe it's not as likely that you're going to get as hot a problem following up to that one. Okay, that's going to be that's kind of where I haven't proved it, but that's where I think the essence of this assumption is. So there's a arrival rate alpha of these new problems, and each time they arrive, they're drawn from some distribution f with density little f. Okay? So when we look at the stationary equilibrium, so in the stationary equilibrium, what we'll have is two things that are going to be stationary. One is allocations are going to be stationary, so M of Z will correspond now to the number of researchers that are allocated to a problem of type C. So that's going to be stationary. I've just eliminated the T sort of index. And this MC, but there are going to be some problems that are going to be problems that are so boring or so low value that nobody takes them. Okay, so only problems above some threshold will be taken, and I'll get to how this threshold is determined. On the other hand, there's going to be an invariant distribution of problems that are available to be solved. Okay? And this invariant distribution will be the result of two forces: the entry of new problems, that is exogenous, and the exit of problems, which is endogenous. And sort of the balancing of those will determine an invariant distribution, a stationary distribution of problems to be solved. Okay? And this, again, will have a density. Only the relevant problems are the ones above that threshold that nobody would take otherwise. So that's sort of the relevant range of that CDF. And of course, and the other side of the CDF, since nobody solves those problems, they'll just pile up to infinity. Okay. So the equilibrium in optimal conditions are exactly the same as what we had before. So I'm just reproducing what the conditions that we had in the sort of non-stationary case. And all what I did is just eliminated the T index. But the interpretation is exactly the same. There's going to be excessive entry into the high C areas in the competitive equilibrium for the two reasons that I mentioned before. Yeah. So what we're going to get is there's going to be a threshold, and actually it's going to be the same threshold. Let's see if I get, I'm going to show you that. It's going to be the same threshold for the competitive and the social planners allocation. Both the M and M tilde Z will be strictly increasing, and though this looks like it can't be, there's going to be they're bigger and they're higher MZ than M tilde Z for every Z greater than the lowest bound. And the reason why this is possible is just because the distribution of open problems in the social planner stochastically dominates that in the competitive equilibrium. And as a consequence of that, the social planner's distribution put more weight on problems that carry more researchers, and that's what compensates the two. So that's but we get, again, the distribution of open problems stochastically dominates, so the social planner sort of reserves more good problems to be solved in the future. So in order to characterize the stationary distribution, it's actually a very straightforward calculation, so I'm just going to go through it, and I think it's sort of interesting. So typically, to characterize an invariant distribution, what you need to say is at every point in the distribution, what enters has to be equal to what exits. So what enters is, with intensity arrival alpha, which is the exogenous arrival of problems, a density FC of problems enters. So that's the entry of new problems. Okay. The exit of problems are with intensity. So take a problem type C, okay? What's the arrival, the sort of solving the problem at time C? It's lambda times mz. That's the arrival, the total arrival rate, or the hazard rate of solving this problem, okay? Take that, multiply by the density of problem Z. This is the total exit rate of problem C. Equate that, that gives you the, that solves directly, given the allocation M and exogenous F, that solves directly for G of C, okay? And this last condition says that really the total relevant problems to be solved, or the new problems to be solved, are those that are above the threshold. The ones that are below that threshold, nobody takes. So the mass of new problems that are coming in, the total, irrespective of their Z, that are relevant, is this, alpha times the ones that are above Z0. And that should be equal to the mass of problems that are going out, which is just lambda times total M, okay, irrespective of the distribution. So notice that this equation determines Z0, the threshold, independent of the allocation. So no matter what allocation there is for MZ, you're going to get the same sort of threshold in a stationary equilibrium. I mean, there's a question of whether a stationary equilibrium might or not exist, okay? So the key here is, again, you know, the social planner leaves more good opportunities for future exploitation. So how much time do I have?
5 minutes.
Okay. So let me not, I mean, I think if I run you through all these equations at this point, you're going to kill me. So let me not do this. It's fairly straightforward. So this is the flow of value. And I'm just going to show you the last equation because I think this is very, I think this is sort of important, and it illustrates really well the idea of value burning. Okay. So this is in the competitive equilibrium. So R of V is the flow of utility, if you want, that is being created. So it's a measure of value. So if you take that divided by R is the welfare, or the total value that's been created per unit of time. Oh, well, per unit of time in this economy by R, per instant of time. And the right-hand side here is lambda M. Lambda M is the total outflow. Remember, you know, in a Poisson, sort of the instantaneous outflow is linear in M. And so lambda, if you take just the sum of lambda times M1 plus lambda times M2 plus lambda, and the M's added to all the endowment, the total outflow, or the total discovery rate, is lambda times M. And this is taking as if you took the total discovery rate and value all those discovery at the lowest bound, at the worst possible problem that is being solved. And so why is this? Because the competitive equilibrium takes care of making all the other problems, through the value burning in the cost, give exactly the same value to the lowest problem. Okay? So this is the equivalent of, in the patent race literature, value burning. Okay? So here I'm going to show a limiting result, the difference between the optimal value and the competitive value. And it's, I mean, lambda over R, this is just because of discounting. Lambda is the arrival rate. This lambda times Z0, all are multiplied by M, so it should be multiplied by M here. So that is lambda times Z0 is what I showed you before. Lambda M times Z0 in the competitive equilibrium. So that's the difference. And this is the expected value of Z is for the social planner. Or if you take the ratio of the two, you get the expected value of Z, conditional on Z being greater or equal to Z0, divided by Z0. Okay. So just to show you orders of magnitude of this, I talked to the patent, to Shankerman, who's, worked a lot on patents and has with Ariel Pecas done estimates of the distribution of patent values and so on. Not sure if the models are consistent or not, but I took that's why I'm not an empirical person. I just took this as a number, and we get that this ratio, as C goes to N0, converges to approximately 6. So the range of sort of difference can be tremendously large, and this comes from the fact that we're looking at a steady state, and we're looking at especially when C is very small, that the most valuable innovations get depleted very, very fast in the competitive equilibrium. And so there are very few remaining in the invariant distribution. And so whereas the social planner keeps them more, longer. And so when you think about the open problems in an economy where we have a social planner that has been doing its job in implementing the optimal allocation, there will be much more interesting problems to be solved than in the competitive allocation. And that's, and the other is that in the competitive allocation, there's so much turnover of researchers because these problems are being solved so fast, and that all that value is burned. And this is what you get. All right, so let me conclude. I mean, there's a part on congestion. The results are very much the same, and so I looked at conditions for excess entry into hot patent races. First, in a static case, showed that it was satisfied with the canonical Poisson model. Then looked at the problem with redeployment and a dynamic problem, and there's an external effect on future values and switching costs. Those are the two, the switching costs or congestion. And by the way, in the case of congestion, when there's no switching cost, the value is going to be burned with congestion. I mean, that's sort of the way that value is equated across them. So either, switching costs or congestion, excessive switching cost congestion, and the no immediate externality, and the option value effect. So I don't know. This is what it is. Okay, from over to
Thank you very much. Have you questions? Not, I have one question.
Okay.
You assume the probability P at the beginning, in the first part of your presentation, is a concave. Is there some evidence that the innovation by researcher is decreasing?
Okay, let me address that. Definitely not. I mean, there could be increasing sort of returns in that P. Let me suppose that P were not concave. So I don't have anything to write here, but if let's say it's logistic, there's a region where it's increasing, so there's some increasing returns, and then at some point it becomes concave. Okay.
That's correct.
Now, if you are looking at the social planners problem, and you take the concave envelope of those, okay, it turns out that so if you take the concave envelope of those, in the social planner, and the best competitive allocation will be operating in the concave part. Okay. And I say the best because what you could have in a competitive allocation is a coordination problem, because if it takes enough researchers to sort of get, to kick and sort of get to an area where it becomes attractive to enter that line of research because of these external effects, if you want, then you might have a zero equilibrium where nobody enters, and you could have like an equilibrium on the concave end. So in some ways, we don't need to make that assumption of concavity. And without concavity, the results correspond to the best equilibrium in the social planner solution.
So I have a quick question about intervention in order to to reduce the gap between the competitive allocation and the optimal.
Okay. So I have two answers to that. One is I think that, of course, if you take literally the model, you could undo it by figuring out exactly how you should, how strong you should make the patents in different areas. So, you should have like a progressive tax on returns, in innovation. But you would have to calculate it exactly. I think a deeper question there is, when we think about innovation and we think about property rights associated to innovation, to get the right level of innovation, we always think about returns to those that solve the problems. Okay? And so we're thinking about how to allocate property rights to the solutions. Okay? Whereas what this says is, well, there is another problem, which is the property rights on the problems themselves. Okay? There are ways in which, there are some responses to this. For example, standards. So when in developing a standard, a set of firms gets together and decides, they're going to develop a standard, and they share, in some sense, share the patents in that standard, but they basically restrict entry. They deciding who belongs to that coalition. Another way might be that firms might try to keep some, like if they do discovering, as the process of discovery, and I mean, this happens to us too. We find that there's a new theorem that you could prove. Maybe you say, okay, I'll wait and try to prove that theorem before putting this in the public domain. I mean, that's in one way of allocating a property right to the problem. So that is part of that. Another thing is that, as I said before, I assume that the ratio between the social value and private, or private and social value, is the same across the problems. There might be some forces that endogenously countervail that, meaning that making that return actually smaller for harder problems. And so, for example, if you think about a quality ladder problem, where there's sort of areas that are hotter, if you want, and will attract more people doing research. Well, that means that any firm that has made a discovery and it's in the lead, it's going to be succeeded faster by other innovators. As a consequence of being succeeded faster, is going to, and if you assume, let's say, that the time at which it gains rent is only through the time up to which it's succeeded, it's going to have a shorter time over which it takes rent.
But you have to introduce another dimension in the problem.
No, I know. What I'm trying to say is that and this is kind of, I think, part of future analysis, trying to understand better, where these problems are coming from, to what extent they are appropriated or not. But I mean, this is present, definitely it's present, for many cases where, and we think of patents as being a mechanism by which firms have an incentive to disclose and put in the public domain their discoveries, and indirectly also in that way, perhaps the next stages and the problems to be solved. So.
Thank you.
Yeah.
If I understand correctly, the set of problems to be solved is exogenous in the whole paper. But we could think that when you solve a problem, you open the door for new problems and probably more interesting problems. So have you thought about how to endogenize the set of problems? I guess it must be very difficult, no? But at the very least, I think that maybe some of these effects are ameliorated, no? Because if in the market solution you have that problems are solved too quickly, but at the same time, is solving a problem open the doors for new interesting problem to be solved? Well, maybe the difference.
Okay, so I mean, I think that points to this distortion that I was talking about, in that 1 minus, instead of being 1, in the competitive equilibrium is 1, in the social planner 1 minus, okay? I mean, that's partly where the source is. Now, the case where you would have the same in both would be if, remember the way I interpret that is that if you solve a good problem, that you're taking away a good problem for the future. But if every problem creates a new problem that is identical to itself, then that doesn't happen. So every time you solve a problem, the distribution of available problems remains the same. It's not affected by that. So that's the extreme case in which this first term that I showed you would be the same in the competitive and the social planner. And that's why I said, well, if there's some mean reversion in the problems, then you're going to have the same qualitative effect. But of course, quantitatively is not going to be of the same order of magnitude.
So I think we have to stop now. So again, thank you very much.